Today we're going to do a little optics 101, and we're going to talk about resolution, depth of field, and try to come up with some practical application and simple understanding of what's going on when we throw formulas up on the board about optics. So the first one that we're going to look at is numerical aperture is equal to n times the sine of omega. Numerical aperture is written on every objective that you use, and it is a very important factor because it's controlling our resolution. N here is equal to the refractive index of the media that we're looking through, which for today and most of our forensic customers is almost always going to be air. But we want to get that numerical aperture number up as high as we can if all we're looking for is resolution. So let's break down that formula and take a little bit of a look at it here. NA is equal to the refractive index of the media that I'm looking through times the sine of the half angle of my objective. Maybe you can zoom down and see or tilt down, Neil, and see this right here. Okay? Again, practical application. The bigger the cone of light that I can gather, the more information that I gather, therefore the more resolution that I achieve. All right? So that's what this half angle is describing, as just half of that cone of light, if you will. And since it's a sine function, we know it's going to run between 0 and 1. You can take a look at that, go through your old math books, but that's the minimum maximum for a sine. So the refractive index of the media that we're looking through, if it is air, is going to be a factor of 1. The sine function has a maximum factor of 1, and therefore the maximum dry objective that I can get would be theoretically have a numerical aperture of 1. In practicality, we find it is more typically 0.95. That objective is capturing light at such a broad cone that even the exact thickness of your cover slip is going to make a difference in the performance of this objective. So oftentimes you will find like a 40.95 objective will have a correction collar on it, where you literally dial in the thickness of your cover slip on your slide to get a perfect match with the objective and achieve the ultimate resolution. Any of you have ever used an oil immersion objective, you say, well, Kevin, they've got a numerical aperture higher than 1, higher than your theoretical 0.95. And I agree with you, they absolutely do. So what have they done in designing that objective? First of all, the objective is designed to work with a specific media. I wrote a few of these over here. Hope they're not getting confused with this formula. But for example, oil has the oil we use for immersion in an objective has a refractive index of 1.51212. 1.51 will work, okay? Glycerin has a refractive index of 1.47, and water has a a refractive index of 1.33. So what happens when we mate one of these higher refractive index materials and multiply that times the sine, we start to get higher numbers. Now we've got a numerical aperture. Typically an oil objective is somewhere between 1.25, 1.30. Typically for years the maximum NA that we could achieve was 1.4. There's some new super resolution techniques used in the biological field where they have very high refractive index medias to look through, and we're able to achieve higher numerical apertures with that. Typically those higher NA or higher refractive index medias tend to be pretty caustic. So these are relatively forgiving and are what we would use most commonly. Okay? So numerical aperture is equal to the media I'm looking through times the sine function. Basically, again, what we're saying is whatever's lying between here and here on the objective, assuming the objective was designed to work with that media, is going to be n. And the sine function, again, is going to go between 0 and 1. Now, I've written this up as though we're dealing with a simple transmitted light objective. If you've got a zoom macroscope like our LCF3, it's got a numerical aperture just like this. In fact, every lens that you use, in fact, has a numerical aperture to it. Typically, it's not something you see quoted on your phone or on a camera lens because resolution at those lower magnifications aren't as critical as it is in the microscope world. All right? So, why do I care about all this? You told me this is important. You told me I want to get this number higher. Why do I care? Well, the reason that you care is over here. Again, my cameraman's coming over. Resolution is typically one of the most important things that we're trying to achieve when we're using a microscope. We're trying to resolve and see more than we're able to see with our naked eye. So, how do we get resolution? Well, resolution is equal to the wavelength of light that I'm using divided by the numerical aperture of the objective plus the numerical aperture of the condenser. And we'll talk about that in just a minute. But I want you all to understand that if you see this formula, I think you're smarter than that. This is oftentimes how the resolution formula is simplified for people, and it really, really bothers me because it doesn't take into effect the functionality of your condenser. Your condenser, or the angle of the light coming into the objective and controlling the angle of that light, is one of the ways that we achieve additional contrast and additional depth. This formula gives you the understanding for that. This formula assumes that you're not smart enough to figure all that out. We're looking at the resolution formula, and remember, we want to minimize resolution. I would rather have half a micron of resolution than 500 microns of resolution. I want to be able to see smaller things. Okay? So, how are we going to get this number to go down? Well, lambda here, and maybe it's too much to look back over here, but lambda is equal to the wavelength of light that I'm using. So in our visible light, that number is going to run between 400 and 700 nanometers. You can specifically control that if you wanted. For example, if I was designing a tool that was trying to do critical dimension measurement, and I wasn't color and contrast and everything weren't as important to me, I would try to use a light that's as close to 400 nanometers in wavelength as possible. Okay? In fact, in the semiconductor industry, they've got tools that are using 365, what's kind of that near UV, that black light that we're used to. I don't remember the other peak, but it's 253 or something of that nature. And they, in fact, are trying to design glasses that will go even shorter wavelengths. Okay? But for our practical purposes here, we're going to deal between 400 and 700 nanometers, and most of us want to see color images, so we're not going to mess too much with this part of the formula. So let's look at the other half of the formula. The numerical aperture of my objective is defined by the type of objective that I purchase for the application that I have. The higher the numerical aperture, the greater the resolution that you're going to get. But the second half of the formula tells us that we also have to pay attention to the light coming from our condenser. And most of you are going to say, I don't know, do I adjust the light coming from the condenser? And the answer is you have that capability with your aperture diaphragm. Okay? That's a little diaphragm that we close underneath our condenser, and as we close it, we gain more depth and we gain more contrast. But you lose resolution. That's what this formula is telling you right here, okay? Because if I don't understand this formula, and I'm going to use this one over here, I can close my condenser all the way, my aperture all the way down and think, hey, I got the best resolution possible. In reality, you don't, okay? Because this formula is telling me that the angle of the condensing light, the light that's illuminating the sample and the objective, is as important as the objective itself. I tried to do a little drawing down here. So I'm in a transmitted light microscope. Up here would be my objective. In this case, I've called it 20x. And then my sample's right here. You'll see I even in my picture drew a blue cover glass. You probably can't see that with that resolution. But cover glasses are huge. They're important. And I always like to mention them and ask people to pay attention to them. But what I have then is an aperture diaphragm. And what it does is it gives me the ability to close down the angle of the light filling this objective. When I do that, I gain contrast and I gain depth, but what do I lose? I lose resolution. And the reason I lose resolution is because at some point, as this light becomes narrower, I can't fill the cone of light. And that cone of light we've already determined, I was going to use determined twice, we've already discussed, determines the numerical aperture of the objective. So this objective, let's say, had a numerical aperture of 0.35. Well, that's all the way out to the green lines that I drew there. As I start to not fill all the way to the green lines, the effective resolution drops, okay? So when I close this condenser down, the aperture diaphragm down in the condenser, I'm closing the angle of light that we see, and as a result of that, I'm picking up contrast and I'm picking up depth, but I'm losing resolution. Consider that you've got a little balance here. Over here I have contrast and depth. Over here I have resolution. Let's call it resolution performance. And I consider them both to be on a balance. When I close down my aperture diaphragm, I improve my contrast and depth. So that's going to go up, and my resolution performance is going to go down. The reverse of that is true, is that as I open that condenser up and I begin to lose contrast and depth, my resolution performance goes up. And I specifically use the word performance here because I'm not talking about the actual number that you're able to resolve. I'm talking about the quality of the resolution, okay? It's the only way this little balance will work out. What am I learning here? Well, you taught me what numerical aperture was, hopefully. And we've learned that some objectives can be designed to look through a media. In the case, again, for forensics, we're almost always going to be doing everything dry. And that numerical aperture is a statement of the sign function of the objective or the angle of the light that it can capture. And that's important to me because I'm concerned about resolution. And resolution is affected by two factors: the wavelength of light that we're using, and the numerical aperture of the objective, and the numerical aperture of the condenser. Okay? Hopefully I've enlightened you enough that you now understand that we don't want to simply say it's 2 times the numerical aperture dividing the wavelength of light, because it's ignoring completely the setting of my aperture diaphragm and the resulting contrast that I see. Now, I drew this in a transmitted light picture because it's the easiest way to explain it to you. But this is true of all of the microscopes that you're looking through. If you've got one of our zoom macroscopes, your numerical apertures on that objective, while they're quite high, 0.15 for an instrument of that type, they don't need structured light coming from them. That's why we don't require a condenser when we're using a low power system like that. But when we close down that aperture diaphragm, it's got the exact same function as it had in a transmitted light objective. As I close that aperture down, my sample starts to gain contrast and gain depth, but it also is going to lose resolution. You'll notice the loss of resolution less at low power than you will at high. Again, if we were to look at a compound microscope, I can open and close my aperture diaphragm probably all the way and not really see a loss of resolution. Well, that's a relatively low numerical aperture objective, and we're not trying to extract a lot of resolution out of it. If we were to do that same thing with a 40x objective, as I close that aperture diaphragm down, suddenly things that look sharp before start to look double-edged, start to look refractal. I just don't seem to be able to define that sample with the detail that I could when that aperture was open. So, am I suggesting to you don't use your aperture diaphragm? No, no. Contrast is huge. The human eye needs a lot of contrast to be able to resolve an image. All I'm suggesting to you is you want to find the right balance between contrast and depth and resolution. Okay? One of the neat things that we have today that we never had in the past, we have the ability to get extended depth of field images through a camera. So now, if all I really need is extended depth of field and it's not as much contrast, we can use electronics to rebuild images and show me that depth. But in pure microscopy, we're always balancing resolution with contrast and depth. Hope that makes some sense. If it doesn't, please send me your questions, your concerns. I'll be more than happy to answer anything that you got out there.